Good evening, Lamai. Right, let's start the class. Today we are going to discuss about benzene, right? It is the benzene chemistry we are going to discuss today, right? Actually, it is at the first tute, right? So we had discussed about the alkanes, alkenes, and alkynes, and we had stopped now, and then we went to the conversions, the compound synthesis processes, right? Next tute, right? Then we'll again coming towards the first tute, right? Benzene. So under the hydrocarbons, there are major four types now, right? Alkanes, alkenes, alkynes, and the benzene. So today we are going to discuss about the benzene, right? The theory stuff appearing with the benzene, right? That is the discussion today, right? Okay. First of all, benzene. So it carries the chemical formula C6H6, right? Benzene is it C6H6 chemical formula, right? So for the benzene, the chemical formula or the molecular formula, chemical or the molecular formula is C6H6, right? When we are seeing this molecular formula or the chemical formula, it appears like we are with some double bonds here, some unsaturated compound. Why is that? Because if it is to regarding as a saturated compound, regarding as a alkane, the saturated compounds are alkanes, no? When the saturated carbons means 4 groups attached to them, right? So if it is to consider as a saturated compounds, it should have how many number of hydrogens? So for alkane, you are with 2n plus 2 number of hydrogens, right? So as the n is 6, you should have 14 hydrogens. You should have 14 hydrogens for 6 carbon compound to be considered as a saturated compound. 2n plus 2 number of hydrogens should be there. But when it comes to benzene, you are lack of hydrogens. You are not with 14 hydrogens there. So benzene is referred to as a unsaturated compound, right? Benzene is referred to as a unsaturated compounds, right? So this formula will give you a right unsaturated compound, unsaturated, right, compound. Molecular formula or the chemical formula, right, with the benzene, right, gives some data that is all about some unsaturation of benzene, right? So benzene is kind of a unsaturated compound. Even though it's an unsaturated compound, right? Unsaturated compound means carbon-carbon 5 bonds are there, right? Unsaturated compound means as you are a hydrocarbon and you are an unsaturated compound, you should think of carbon-carbon 5 bonds, right? You should think of carbon-carbon 5 bonds, right? But this benzene is not going to give the positive results for the test for unsaturation. For the test for unsaturation, so we know with alkenes as they are unsaturated, Br2 will react with that. Br2 will react to form the dibromo product, so that as Br2 consumes, the color of the Br2 disappears. So that is one unsaturated test for unsaturation, right? Adding Br2. If you are with the unsaturated carbon-carbon bond, as Br2 is going to react, right? The color of the Br2 will disappear, right? Is one test to identify the unsaturation for the carbon-carbon 5 bonds. So another test is there we had discussed. So with alkenes, you can think of adding basic KMNO4. The KMNO4 is colored purple in color. If you add the basic KMNO4 to alkenes, where you find the carbon-carbon 5 bonds, what will happen? As the KMNO4 reacts with that thing to produce the diol, right? As the KMNO4 consumes, the color of the KMNO4 disappears, right? So those are the major two tests we can use to identify the carbon-carbon 5 bonds. The presence of carbon-carbon 5 bonds can be identified by adding Br2O basic KMNO4, right? So those are referred to as tests for unsaturation, right? Okay. Or one can say the identification of carbon-carbon 5 bonds, right? So when it comes to benzene, when it comes to benzene, we are expecting benzene to react with those and give those expected results. But when it comes to benzene, so I'll write it as C6H6. The benzene, even though it is unsaturated, it won't give the positive results for the test for unsaturation. So if you are to add some Br2 in organic layer, we expect the Br2 to react with benzene as it's a unsaturated compound. But you won't see any kind of change there. So no change. Even with the OH minus K form. No change. That means no change means no reaction. Right? So we have problem. Yes, benzene is referred to as an unsaturated compound. Then why the benzene is not going to give you the results for the unsaturation? Not going to give you the results for the carbon-carbon 5 bonds. Right? There's a problem. Special compound, no? That's it. So another very important observation with the benzene is actually, if you are to think of the bond distance between the carbons, if you think of the bond distance between the carbon atoms of benzene, bond distance between carbon atoms of benzene, right? Actually, that resides, or that comes up with some value which is in between the carbon-carbon single and the carbon-carbon double. Right? The benzene's carbon-carbon bonds, the length or the bond distance resides between the carbon-carbon double bond and the carbon-carbon single bond. That those values. The carbon-carbon single bond is with 154, no? And the carbon-carbon double bond is with 134. Those are the major values, no? So this is with 134 picometers. This is with 154 picometers. But the benzene's carbons with benzene, carbons of benzene are with some bond distance of 139 picometers, which is actually in between the carbon-carbon single bond value and the carbon-carbon double bond value of hydrocarbons. So this also says that benzene is having a special kind of bond which is neither a double bond nor a single bond, right? So actually benzene is with some carbon-carbon bonds which are with both the double bond and single bond characters. So it's a kind of a mixture, some hybrid nature is there with benzene. That is what we can ultimately think of, right? So benzene is carrying such kind of carbons. So with these observations, right, scientists were thinking of what kind of bonds appearing with the benzene, right? So then they came up with these ideas, right? So what are the ideas? First, the first scientist to propose a structure for benzene is actually the Kekulé. The scientist Kekulé. So scientist Kekulé came up with a structure for the benzene like this. So he said the benzene should have this kind of structure, right? Benzene should have this kind of structure. That was the first proposed structure for the benzene. This structure proposed by Kekulé. Thinking of the unsaturated nature, he proposed the benzene should be a hybrid of two resonance structures. Should be a hybrid of two this kind of resonance structures, right? So you can think of like this. the two CCH6 resonance structures, right? This was the first proposed structures for the benzene, right? So they say the benzene is a resonance hybrid of these two resonance structures, right? That was the first idea, right? Benzene is a resonance structures of resonance hybrid of these two resonance structures. These resonance structures are referred to as Kekulé structures. These are referred to as Kekulé structures, right? Kekulé. That was the scientist first came up with this proposal. So we can say benzene is a hybrid of two Kekulé structures, right? So that is the idea. So then for the convenience or simpleness of writing the stuff, right? They had done some changes, right? They had done some changes in the purpose of writing the benzene, right? So this is the these are the Kekulé structures. Benzene is a hybrid of these two guys. So one can represent that thing as this. The hybrid can be represented like this. Right? One can represent the hybrid like this. Hybrid, no? Six carbons are appearing at the six corners. Right? So you can represent the hybrid like this, right? The hybrid. Hybrid of Kekulé structures, right? So this is the benzene. Right? The most convenient form is this hybrid. So you don't have a double bond here. You don't have a double bond here. It's a 1.5 bond order with these base bonds, right? The double bond could be here as well as here. At the other instance, it could be here, right? Like this. So 1.5 kind of a bond appearing with the benzene. That is why these guys are not reacting to Br2. Actually, no complete double bond is there. So not reacting to Br2 as well as basic KMNO4, right? Because of this nature. No complete double bonds are there. So half a double bonds. So that is a partial double bond character. You are not with complete double bond. It's a partial double bond character appearing with the benzene stuff, right? So this is the hybrid. So then scientists thought of writing these things in simpler manner. So then what they have done? What they have done is, right, they thought of writing this thing simply. So first of all, they have written, right, this stuff like this. To simplify the structure, they have ultimately, right, remove the carbons and hydrogens from the picture, and they have just written like this. No need of writing the carbon and hydrogens, right? For the simplification, right? Then they have written that hybrid nature by just adding a round shape to the center. So ultimately, this is the benzene now. Nowadays, this is the symbol we use for benzene. And remember, this is the actual structure, right? This is the actual nature of the benzene. But for convenience, for easiness of writing, we come up with this kind of a symbol for the benzene. So now the benzene is referred to as this CCH6 or the benzene. Right now, so this is the structure for the benzene, right? Okay, so this is benzene. So all this story is there at the page number 28, right? What I have told you, right? Let's go to that, right? බලන්න. හරි. Okay නේද? Let's go to the node there ළමයි. Just go to that and see. ළමයි, at another point is there at the node, right? It is said that the resonance structures or the Kikuly structures are known as cyclohexatrienes. That is okay, no? The Kikuly structures are known as cyclohexatrienes, right? I'll discuss that thing later, right? So, and then the name given to the Kikuly structures, right? Cyclohexatrienes, right? We'll discuss that thing later, right? So that is all about the page number 28, the things appearing at the page number 28, right? Okay, you can go through that, right? Then let's move to the page number 29, right? What they are saying, right? These are some stories, right? Not that much needed. Not that much questions will be asked from the stuff just we have learned, right? But that is for the as we are, I'm trying to introduce the benzene to you. I had to say these stories, right? Okay, so this is just the introduction of the benzene, right? So as you know, what we are doing is basically first we are introducing the compound, no? Then we are discussing about the production techniques, and finally we are going to discuss about the reactions involved in the compound, right? That those 3 steps are followed, no? When discussing about a compound here, right? So there's the introduction, right? Okay, few more stuff to be discussed with the introduction. Let's go to those things quickly, right? So let's discuss how the bonding nature, how the bonding picture appears with the benzene, right? So the benzene is look like this, Lama. So the actual picture, right? The hybrid picture looks like this. Basically 6 carbons. If you have to think of 6 carbons, all the 6 carbons of benzene appears at one single plane. That is very special with the benzene, no? All 6 carbons of the benzene appears at one single plane. One single plane, no? This is very important stuff in the benzene, right? So at the hybrid, all the 6 carbons of the benzene appears at one single plane. Even the 6 hydrogens, all the atoms of the benzene appears at one single plane. Remember that. Kind of special stuff with the benzene, right? All the 6 atoms of the benzene appears at one single plane, right? Okay. So for easiness of drawing, I'll just erase the hydrogens, right? So we have 6 hydrogens as well, right? Okay, right. In the same plane, right? All these dual atoms in benzene appears at the same plane, right? So then we could think of the 5 bonds here. We could think of the p orbitals appearing on these carbons, right? So this picture is there in your note. Just prefer that. Right? These are the 5 orbitals. So the thing is, at your resonance hybrid, right? At your resonance hybrid, these guys are connected. These guys are connected, right? All the 6 lobes appearing at the top, right? Will be connected to each other like this, as well as all the 6 lobes from the bottom also connected, right? So like that, kind of cyclic delocalized electron cloud appears in benzene. Cyclic delocalized electron cloud appears in benzene, right? So 6 carbons at the same plane, right? You are with 6 carbons at the same plane. This is the plane of benzene, right? So from the top and the bottom of the plane, right? Electron densities are connected. The 5 electron densities are connected, right? If you see the stuff like that, so it's like you have a plane like this, one single plane, right? From the top and the bottom, you have the 5 electron densities. This is a plane of carbons and hydrogens. From the top and the bottom, you are with some 5 electron cloud, right? Some electron rich nature is there from the top and bottom of the plane. So that the electrophiles will clearly attack to benzene from the top and the bottom of the plane, right? So that is the structure, that is the 3D structure of benzene, right? This is your plane, and from top as well as from bottom, the lobes are connected, right? On the bottom, these lobes are connected, right? As well as from the top, right? These things are connected as well as these things, right? From the top and the bottom, you would see some electron density appearing, right? That is how the benzene is appearing, right? Okay, this is the benzene. So you can clearly see at the note it is said all carbon atoms in benzene are sp2 hybridized. That is understood, no? sp2 hybridized. No, only 3 bonds are there. No? sp2 hybridized. So these are the hydrogens. No? So the guys are sp2 hybridized, right? 1, 2, 3 sigmoids. No? sp2 hybridized, right? And each carbon bears an unhybridized p orbital, which can overlap with the unhybridized p orbitals on either side of it. Each carbon atom bears some unhybridized p orbital, right? Those will overlap with either side, right, of it, right? From this, a cyclic delocalized electron cloud common to all 6 carbon atoms is formed. Cyclic delocalized electron cloud like this. Which is common to each carbon. 6 carbons are formed, right? So, and ultimately it says benzene shows showing lateral overlap of p bonds, p orbitals, sorry, forming a cyclic duration is that picture is given, right? So that is the idea, right? Just some picture, right? That is benzene. This is benzene, right? Okay. Let's discuss about few more on benzene, right? Next, with the tute, right? Some energy diagram is appearing. Let's discuss about that thing as well. In 2020 question, right? That was asked, right? What was that? So let's come up with the resonance stabilization. Let's discuss about the resonance stabilization of benzene, right? So we know that benzene is a resonance hybrid. So let's discuss about the resonance stabilization, the stability of benzene attained by the resonance, right? This is about that thing. Stability of benzene gained by resonance, right? Let's discuss about that thing, right? You can come up with this energy diagram, right? Practically, they have found that if you are to hydrogenate, this compound, by adding adding H2, they have found, right, the energy needed to hydrogenate this. That means to connect 2 hydrogens to this one, right? They have found that the energy needed is 120 kilojoules. These are some practical data they have obtained, right? And they have found that to hydrogenate the benzene, to add some hydrogens to benzene, to come up with this, adding hydrogens to benzene, right? Right, it required 208, no, 208. These are some practical data, right? We are supposed to come up with the resonance stability of benzene, right? So let's use these two data to think of the resonance stabilization, right, of benzene, right? Actually, when it comes to calculus structure, you have 3 of these. Right? You have 3 of these, right? So if you think of the Kekulé structure is like this, no? Kekulé structures are like this, right? Kekulé structure, right? If you have to hydrogenate that thing, you need 3 of H2s. You need to do this process thrice to completely hydrogenate the cochlear structure, right? That will need 120 into 3, 120 into 3 amount of energy, right? For cochlear structure hydrogenate කරන්න එක CVCO 3ක් ඕනේ to produce this one, to produce this structure, to come up with 6 hydrogens here like this by a cochlear structure. To produce this thing, you need 120 into 3 amount of energy, that is minus 360 kilojoules per mole. This is the energy required, the energy gap between the Kekulé structure and this structure. This is now referred to as what? This is referred to as cyclohexane. To convert the Kekulé structure to a cyclohexane, this amount of heat change is needed, right? But to convert the benzene to cyclohexane, you just need 208. The energy gap is that 208. So the benzene thing should occupy this space, right? This kind of a space. So this is about hydrogenating benzene to Kekulé structure, sorry, to cyclohexadiene. This need just minus 208, right? This is the benzene. Right? With this, you clearly see the benzene is more stable than Kekulé structures, right? So benzene is less energy than the Kekulé structure. According to this observed data, we can construct this energy diagram. So the energy diagram says the benzene is with less energy than the Kekulé structure. That means the benzene is with some greater stability than the Kekulé structures. Right? Benzene is with some greater stability than the Kekulé structures. Less energy means more stable. Less energy means more stable, right? So with this diagram, we can clearly explain that benzene is more stable than Kekulé structure, and that is due to the resonance stabilization. It is due to resonance stabilization, right? With Kekulé structure, the structure is this, but benzene comes as a resonance hybrid. So the hybrid is more stable than the existing more stable than the Lewis structure, right? So naturally existing structure or the hybrid is more stable than the one of the Lewis structures contributing to that, right? So that gap, that energy gap is referred to as the resonance energy, the resonance stabilization energy. So benzene is more stable than the Kekulé structure by how many units? The gap between these two is actually what? That is 152. So benzene is stable than the Kekulé structure by 152 kilojoules. 152 kilojoules per mole. So this 152 value is referred to as the resonance stabilization energy of benzene. This 152 value is referred to as the resonance stabilization energy of benzene, right? Okay. So in 2020 paper, they had asked this question, right? What is the resonance stabilization energy of benzene? They have provided these two things, and they have asked you to construct it energy diagram and calculate the answer. This diagram is clear, no? So this is the energy needed to convert the Kekulé structure to the cyclohexane. To convert the Kekulé structure to cyclohexane, you need to hydrogenate 3 of the 5 bonds. 3 of the 5 bonds. So one 5 bond needs 120 energy. So 3 of the 5 bonds needs 360 amount of energy. This is the energy involvement when hydrating all the bonds of the calculus structure to create the cyclohexane, right? Then when it comes to benzene, to hydrate benzene completely to the cyclohexane, they have provided this energy is needed, right? Okay, so that is that energy 208. So with this diagram, you clearly see the benzene should appear below the calculus structure in energy, right? So you have a difference of 152 kilojoules between the calculus structure and the benzene, and that is referred to as the resonance stabilization energy of benzene, right? No? So that is the idea. So the thing is there in your research book. Just go through that. No, in your note, just go to right at the page number 29, right? So this is regarding that. So at the bottom they had said, right, benzene is more stable than its calculus structure by an amount equal to 152 kilojoules mole. This stability is due to the cyclic delocalization of 6,5 electrons, and it is termed as the resonance stabilization or the aromatic stabilization energy of benzene, right? This number is referred to as the aromatic stabilization energy of benzene, right now. Okay, that is all you should know about the benzene as an introduction, right? So that we have just completed the introduction of the benzene. Benzene introduction තමයි අපි කතා කරලා ඉවර කරේ, right? හරි. මේ ගැන මොනවා හරි ප්‍රශ්නයක් තියෙනවද ළමයි? අපි දැන්ට කතා කරපු දේවල් සම්බන්ධයෙන් පොඩ්ඩක් කම්මැලි කේස් එකක් තමයි මුල් හරියන්නේ. ඊට පස්සේ වැඩි පටන් ගන්න හරියට. So do you have any problem appearing with this? මේ සම්බන්ධව ප්‍රශ්න දෙන්න. පහන්. නැත්නම් එහෙම උලක් නැද්ද? No worries. හරි. අපි එහෙනම් වැඩි ඉස්සරහට යන්න. සාමාන්‍ය මේ නෝට් එකේ තිබ්බ පොඩි පොඩි කාරණා ටික හොදේ. ඔය වැඩි අහන්න යන්නේ ලොකු ප්‍රශ්න අහන්න තැන නෙමෙයි. කියන්නේ දැනගෙන ඉන්නක හොඳයි ලාවට දැනගෙන ඉන්න හරි. මේක නම් අවුරුද්දක් ඇහුවා. 2021 පෙබරේදී අහුවා. මේ ඒ අරින් තුරු ටික නම් ඉතින් අහන්න නෑ simple stuff, right? Okay, let's discuss about the production techniques there. Production techniques of benzene, right? So, no worries, ne? Production ne? හරි. අපි යමු එහෙනම් කතා කරන්න production techniques, right? So, production of benzene. Now, when benzene produce කරන්න තියෙන විදි දෙකයි. There are only two methods available to produce benzene, right? Let's discuss one by one. The first method of producing benzene, right? So you could count like this, right? So you could think of a benzene grenade. So you could have a benzene grenade, right? So let's say you have with a benzene grenade, some MGBR section connected to the benzene. If you had this kind of stuff, right, and if you're supposed to add some H plus H2O, if you're supposed to add some H plus H2O to that thing, then not to 11. As this carbon is negatively charged, because the electrons are attracted towards the magnesium, no? Electrons are attracted towards the magnesium, huh? Because the magnesium is sorry, not that. Electrons will be attracted towards the carbon, right? Electrons will be attracted towards the carbon because magnesium is with 1.2 affinity. The carbon is with 2.4, no? 2.5, no? So electrons are attracted towards the carbon. So the carbon is carrying some negative delta. So that will attract ultimately the positive hydrogen, right? That will attract the positive hydrogen. So the MgBr leaves and hydrogen will connect. MgBr leaves and hydrogen will connect, right? So we'll come up with benzene ultimately. That is the first method of producing benzene from other compounds, right? So first of all, you should have a benzene ring appearing with the MgBr. Then if you are at the H plus H2O, you will get the benzene. One can add the D plus D2O as well. Not only H plus H2O, D plus D2O can be added. What is D plus D2O? D means that is the heavy water, the heavy hydrogen. D2O is the heavy water. Deuterium, deuterium, right? You can, instead of H plus H2O, you can come up with the D plus D2O. The hydrogen and deuterium both are with the same chemical properties, right? Chemical nature is same, no? Electronic structure is same with the hydrogen and deuterium, no? But differs is just the number of nuclear particles. One neutron is right more with D plus, right? You have some excess of electron and excess of a neutron with the deuterium, but the electronic structure of these two guys are same, right? So the reactivity is same, right? So you can add the D plus D2 as well instead of the H plus H2, so that what will happen? So that you will come up with some D here instead of the hydrogen. Some deuterium will be added, D will be added. Earlier I have not written the hydrogen here because all the with all the carbons the hydrogens are appearing. No use of writing the hydrogen again, no, right? So here, as it is a different atom, it's not the hydrogen, it's deuterium. I just written that, right? So you can come up with this kind of a structure if you add some D plus D2, some heavy water, acidic heavy water, to Grignard containing a benzene ring, right? So this is the first method region which you are supposed to form the benzene, right? Okay, that is appearing there with your note at the page number 30. Just complete this stuff, right? The MgBr thing can be connected to benzene or can be connected to deuterium, right? Just complete this thing. And with that, I'll come up with the second way of producing the benzene as well. The second form is actually you can come up with this compound. This is a very special compound. Right? This is known as benzene diazonium salt. Is known as benzene diazonium salt, right? Benzene diazonium salt. Earlier it was the benzene Grignard, right? Benzene Grignard. Now it is the benzene diazonium salt, right? So if you are to add this H3PO2, right? If you are to add this H3PO2 and some water, H3PO2 and some water to this benzene, to benzene diazonium salt, you will come up with benzene. That is the second method of producing benzene. Only these two methods are there appearing with our A-level syllabus, right? Only two methods are there to come up with the benzene ring. You should come up with benzene magnesium bromide or the benzene Grignard, or you have to come up with the benzene diazonium salt. This is referred to as benzene diazonium salt. When this N2Cl part appearing with a R group or with a benzene, those are referred to as diazonium salts, right? Diazonium salts. So these are the two methods available to produce the benzene, right? So you can complete this stuff. ටක් ගාලා මේ දෙක ඇඳ ගන්නවා. ස්පේසස් දෙකේ. ඔය තමයි බෙන්සීන් එක හදාගෙන තියෙන ක්‍රම දෙක. right? හරි. Those are about the production techniques of benzene. Here this is H3PO2, right? H3PO2. Just remember that. It is not the H3PO4. H3PO4 is the most commonly used acid of phosphorus. But here the H3PO2, right? It is easy to remember this thing by remembering the oxidation state of phosphorus here. The oxidation state of phosphorus here is just +1. Oxidation state of phosphorus is +1. Right? So +1 and +3 will give you +4. That will be cancelled off by the -4 of the two oxygens, right? So H3PO2, that should be the one to add. It is not the H3PO4, right? It is H3PO2. H3PO2 and water. Right. එහෙනම් අපි යමුද ඊට පස්සේ බෙන්සීන්ගේ reactions කරා. Let's discuss about the reactions involving benzene. බලමු benzene reactions මත ගිහිල්ලා මොනවාද මේ benzene කර reactions කියලා. right no? මේ diazonium salt එක අඳින්න ළමයි මේ විදිහටම charges දාගන්න. The plus charge should appear on this nitrogen, not here. The nitrogen which connected to the benzene ring. And the minus charge appears on the chlorine, right? Diazonium salt, benzene diazonium salt. Right. Let's discuss about the reactions of benzene. Reactions of benzene. Reactions of benzene. Right? Reactions of benzene. First, let's discuss about the characteristic reaction type. Characteristic reaction type. Characteristic reaction type. We had discussed this thing earlier. Again, just quickly go through that. So what we can say? So basically, when it comes to benzene, it is a very dense 5-electron cloud. It's a dense 5-electron cloud. So that what will happen? So that electrophiles, electron loving groups, the electrophiles will attract to this. Electrophiles will attract. Electrophiles will attract. Electrophiles attract to benzene ring. So electrophilic reactions. So we are thinking of electrophilic reaction, right? Then these carbons in benzene, the sp2 carbons in benzene, actually those carbons in benzene are unsaturated. Carbons in benzene are unsaturated. So that we are thinking of addition reactions. So normally with unsaturated carbons, additions are preferred. Right? Addition reaction. But the benzene is actually BIP. And we had discussed this thing earlier as well. The benzene is actually BIP, right? So what happens? Even though additions, right, are the ones which will be carried by the unsaturated bonds, unsaturated carbons, in benzene, additions won't occur. Benzene undergo substitutions. Why is that? So you should know the reason as well. This is VIP, yeah. This VIP. You should know the reason. Right? The reason is what? The reason is actually benzene is stabilized by a delocalized electron cloud. So benzene is stabilized by delocalized 5-electron cloud. Aromatic stabilization. Right? So benzene is stabilized by aromatic delocalization. of conjugate 5 bonds. Or conjugate 5 bond electrons. Right? So benzene is keen to be with that stabilization, and benzene refuses reactions which will affect the stabilization. Right? So benzene prefers to maintain that stabilization into that stability and refuses reactions which harms which harm the resonance, which will harm the resonance. Right? Which is reactions which harm the resonance. Right now? So that is the situation with the benzene. So that we can say the characteristic reaction type is electrophilic substitutions. So the characteristic reaction type is electrophilic substitutions, right? So electrophilic substitutions. Right? Those are the characteristic reaction types of benzene. So that is clear. So that thing is appearing at your tute at the page number 30. Let's go to that and see whether you got the idea. Right? It says benzene contains loosely bound delocalized electron cloud on both faces of the planar benzene molecule. Right? This makes benzene ring electron rich and hence reactive towards electrophiles, similar to alkenes. So the electrophiles will attract. Right? Then it says benzene shows extra stability due to delocalization of electrons. Therefore, benzene does not easily undergo reactions which destroy the cyclic delocalization, which harm the cyclic delocalization. Then benzene won't prefer those reactions, right? Hence, the characteristic reactions of benzene are electrophilic substitutions and not electrophilic additions reactions, as in the case of alkenes. Right now, the idea is clear. No? So, electrophilic substitutions are the major reaction kind or the characteristic reaction kind of benzene. Right? Okay. Let's move towards the reactions one by one. We had discussed about the characteristic reaction type. Now let's move towards the 4 major reactions available with the benzene. Right. So electrolytic substitutions are the characteristic reaction type. So let's see what are the reactions available then as electrolytic substitutions. Right. So electrophilic substitution reactions of benzene. Right. There are 4 such kinds are there. Let's discuss one by one. Right. Halogenation, number 2 Fieldcraft alkylation, then the Fieldcraft acylation, right? Acylation. Number 4 is the benzene nitration. These are the 4 major type of reactions we will discuss with benzene, right? Okay, we need to discuss the reactions as well as their mechanisms as well. So each and every paper, either paper carries these 4, one of those 4 reactions as well as its mechanism, right? We'll discuss. So actually, first before going to discuss about one by one, let's discuss a bit about what this happens here. So it is like this, Lama. So benzene, we know that benzene is kind of a unsaturated compound now. So I'll just write this hydrogen, one of the hydrogen here, and we know that the characteristic reaction type is electrophilic substitution now. That is what we are discussing now, right? So what happens is this. So basically, the electrophile will come towards the benzene ring and replaces this hydrogen, one of the hydrogens. Electrophile will replaces one of the hydrogens, right? You are with 6 hydrogens here with the benzene CCH6. So at the electrophilic substitution reactions, this new coming electrophile will replace one of these hydrogen to connect to the benzene ring. That is what substitution means. That is what substitution means. Instead of the hydrogen, the electrophile will be added. Right? This is the simple form of representing these tertiary substitution reactions. Here, when regarding the halogenation, E plus is equal to Br plus. Halogenation means you are just trying to connect some halogen, right? It could be Br plus or Cl plus for the halogenation process, right? When it comes to alkylation process, the one which is going to connect is actually a alkyl group. Like this, you can think of any kind of alkyl group. The electrophile is going to be a alkyl group, right? So if you think of acylation, electrophile is going to be a ketone group, right? So ketone group, right? If you think of nitration, the electrophile is going to be a NO2 plus. So those are the major 4 types of electrophiles coming towards the benzene ring and connects to the benzene ring by replacing the hydrogens, right? So this is the general form of tertiary substitution reactions at the benzene ring. So one of the hydrogen will be released by substituting an electrophile. In bromination, this kind of electrophile will be connected as a bromine atom or a chlorine atom when regarding the chlorination. In alkylation, the alkyl group, one of the alkyl groups in the alkyl group will connect by releasing the hydrogen. In acylation, kind of a ketone group will be connected to the ring, and in nitration, the NO2 group will be connected to the ring, right? So we'll discuss one by one now, right? We'll discuss the reactions as well as the mechanism one by one. Let's start with the halogenation, right? Let's start with the halogenation. So here we are referring to electrophilic substitution reactions of benzene. They are under that. First, now we are starting discussion about the bromination. or the halogenation. As an example, let's come up with the bromination reaction. Benzene bromination, substituting a bromine atom instead of the hydrogen, right? This is about this thing, right? So the reaction would look like this. Reaction would look like this. Connecting a Br atom, halogen atom. Connecting a Br atom or the halogen atom instead of one of the hydrogen. This is the bromination. This is the bromination, right? To do this thing, right? We need to add Br2. We are going to add Br2 in the presence of anhydrous FeBr3 catalyst. Right? That is a reagent, right? To connect Br group to the ring, right? You need to add Br2 in the presence of FeBr3 catalyst, right? With this reagent, you are able to connect a Br to the ring, right? Let's discuss about the mechanism of this thing. Mechanisms are very needed, huh? Frequently, the mechanisms are asked in A levels, right? The benzene mechanism. So let's come up with the mechanism. Mechanism of this stuff, right? Okay. So actually, benzene mechanisms are with 4 steps. Benzene mechanisms are with 4 steps. All the mechanisms are with carrying these 4 steps, right? One after the other. With that order, same order, the 4 steps are happening to come up with the ultimate product. Let's discuss about those 4 steps of the mechanism. The first step is all about. The first step is all about, right? Reaction of these two guys to come up with the active catalyst, to create the active catalyst. That is the first step, right? So we can write it as reagent reacting with right catalyst to produce active electrophile. That is the first step. Reagent reacting with the catalyst. These two guys are reacting to produce the active electrophile. Let's write that stuff, right? So it will be like this. So you have the Br2 and the FeBr3, the catalyst. So what happens is these 2 electrons will be donated to this one. So that will produce this kind of a compound, right? As this is a dative bond, the dative bond donor gets a positive charge and the dative bond acceptor gets a negative charge, right? So this is referred to as the active electrophile. This is referred to as the active electrophile, right? In this case, as FeBr catalyst accepted and lone pair, it is also referred to as a Lewis. It is referred to as a Lewis acid. Lewis acids are the ones which accept lone pairs. Lewis acids are the ones which accept lone pairs. So In this mechanism, FeBr3 is referred to as a Lewis acid. Right now, this is the formation of active electrophile. Right. Let's copy the second step. Let's copy the second step. Right. So the second step is actually benzene reacting with the active electrophile. So benzene reacts with the active electrophile to produce uranium ion. Right. Let's discuss about that step. So this is what happens. Right. So now benzene comes to that. Right. Okay. So what will happen? So benzene is with these 5 bonds. Right. It will attack to the so produce active electrophile. So you have with these things like this. You have plus here, minus here. No? So as this is positively charged, now you have a difference in electronicities between the two bromines. So what will happen? These electronicities are heavily attracted towards the positive bromine, as it is with greater electronicity than this bromine. So you will create a greater positive charge with this bromine then. So towards that positive charge, the ring electrons will attract. Right? As you have with a positive charge here, because the electrons are attracting towards the Br heavily. So towards this delta positive charge, these electrons will attract. So what will happen then? From that electronic movement, from actually after this electronic movement, Br will leave its electrons to this, right? When this attack happens, Br will leave this electron pair to Br plus. Because when this bond is formed, this bond is left, right? Okay. So you will come up with this compound then. You will come up with this one. So this will be will come up with some Br. That hydrogen is also appearing, right? The hydrogen which is supposed to leave. Just so you need to write that thing as well. And to this place, a positive charge comes. Just remember the mechanism of Br2 addition of alkene. Just remember the Br2 additions of alkenes or the HBr additions of alkenes. Just remember the HBr additions of alkenes. When the electrophiles connect, to one of the carbons which were with the double bond, when the electrophile connects to one of the carbons which earlier with double bond, the other carbon gets a positive charge, right? The other carbon gets a positive charge. That is what happens here, right? Okay. When the electrophile connects to one of the carbons which earlier had the double bond, right? When the electrophile connects to that, the other carbon which was with the double bond gets a positive charge, right? That is what happens here, right? So, and this thing will leave. This can be written as right? Actually, Br, FeBr, some minus here. That is the idea, right? Okay. So that is what it produces, right? So one can write like this thing as FeBr4 minus. Both are same, right? One can write like this as well, right? No worries. This form or this form. Next one. Third step. Right? And this is referred to as the arrhenium ion, right? Before that, this is referred to as arrhenium ion. Uranium ion. It's a carbocation, right? It's a kind of a carbocation. Right. Next step. Step number 3. Right. Next step is actually the resonance stabilization of the co-produced uranium ion. Resonance stabilization of the co-produced uranium ion. That is the third step. Right. Resonance stabilization of co-produced uranium ion. Actually, which is a carbocation, right? Uranium ion is kind of a carbocation, right? Okay. Let's do the stuff. So uranium ion will be stabilized by the resonance. Right? So it's like this now. So you had a hydrogen here, Br here, positive charge here. Total up. To neutralize the positive charge, right? This pair will come towards here. This pair will come towards here. So that actually what happens is actually the electron from here, the 2 electrons are there here and here. No? So this electron comes towards here. This electron comes towards here to neutralize the positive charge and form the bond. So you have electron here, and this electron come to here and forms a bond. So the positive charge disappear, and here a positive charge will form. As this carbon loses this electron, here a positive charge will form. Right. So the resultant structure is like this. Have this thing here, the bond, newly formed bond, but you are with a positive charge now here. Hydrogen is there, Br is here, and some double bond here as well. Right now, okay. So then, what will happen? So neutralize the positive charge, neutralize this positive charge, right? These bonding electrons will come towards here, right? That bonding electrons will come here. So that what will happen? So actually, what happens is this electron of the bond first come to here. This electron of the bond first come to here and form the bond at this place. So they are this carbon gets a positive. This carbon gets an electron, so that the positive charge will disappear with this carbon. But as this carbon loses an electron, there you will find a positive charge with this resultant structure, right? So let's do the one. The H and Br appears like this. So this bond is there. So what happens is when this electron comes to here, the positive charge of this carbon disappears, and a bond will form here, and the positive charge appears here as this carbon loses its bond, right? Okay, those are the resonance structures, and that is how the uranium ion is stabilized by the resonance. This is how the uranium ion is stabilized by the resonance, right? So you can write this thing as well after that. Right? This is the resonance stabilization of the uranium ion. Right? Final step. The final step. Right? So do I have space to copy the final step? Yes, I'll write it here. The fourth step. Right? It is the regeneration of the catalyst with the product formation. Right? Let's write that thing. It's referred to as the regeneration of the catalyst with the major product. That is the final step, right? Let's try to do the step. Okay, let's copy the that step, right? So these are final step. So you had a positive charge here, right? Just start with here, am I? Just start with the same array mine, right? You had a positive charge there. Hydrogen is there, and a Br is there. So what happens is this cell produce FeBr4 minus, FeBr4 minus attack this hydrogen. So you have the FeBr4 minus like this, no? Right? That thing will attack this hydrogen with this bond. It will attack this hydrogen. So that hydrogen will leave this bond. Hydrogen will leave this bond to this space. Hydrogen will leave this bond to this space, right? To form the benzene again. To form the benzene again. Simply this electron will be given to here. This electron will be given to this carbon to form the 5 bond. The one electron is here, no? This electron will be given to this carbon to form the 5 bond to complete the benzene ring, right? So this positive charge will disappear, and so that the hydrogen will leave with this Br. These electrons pair will grab the hydrogen, so that the hydrogen will leave as HBr, and these electrons will be given to here, so the benzene ring will be formed as the major product, right? So the products are the bromobenzene, benzene with the bromine, and HBr, and this thing, that thing will be left as FeBr3. This thing will be left as FeBr3 because the negative charge of the fluorine, Fe, will also disappear. Because as Fe loses this electron, the negative charge of the Fe also disappears, right? So the final products are, the ultimate products are benzene with the Br and the HBr and the FeBr3, right? Benzene with the Br and the HBr and the FeBr3. So you clearly see the catalyst is produced again. The FeBr3, the catalyst is produced again. The FeBr3, right? Catalyst means that no net consumption or production. So the consumed amount is regenerated, right? So your catalyst is there, right? Right. So that is your mechanism. So major product and the catalyst are formed, right? This is your major product. This is your major product. Right. So that is how the bromination occurs, right? Just go to this level. Medical लिया करना shape पे. I'll give you 2-3 minutes. Come on, shape එක लिया කරන්න. හරි. මොකද නෝ ඊළඟ mechanisms ඔක්කොම ටික මේ වගේම තමයි යන්නේ. මේ steps හතරම තමයි follow වෙන්නේ හැම mechanism එකක් එක්කම. right? ඒක නිසා එකක් හරියට තේරුම් ගත්තා නම් වැඩේ කරගන්න පුළුවන්. හරි. මේක ලියා ගන්නකො. That some space is there with the page number 31. Just try to complete the mechanism as well. Reaction එක ලියලා mechanism එක ලියන්න steps හතර. This is halogenation, right? දැන් පොඩ space manage කරගන්න වෙයි මේ half of page වගේ අරගෙන මේක ලියාගන්න වඩා හොඳයි. මොකද අපි mechanism set එකක්ම ලියන් තියෙනවා pages දෙකක් වගේ තියෙන half page වලට වගේ ලියාගෙන try එකක් දෙන්න බලන්න. So you have the benzene, right? You're supposed to create some alkyl group there. You're supposed to create some alkyl group like this. Let's say CH2CH3. Some alkyl group is to be connected, right? So to connect this kind of alkyl group, right? To connect this kind of alkyl group, what we need to add is this group with some halogen here, By leaving the halogen, this carbon connects to the ring. By leaving the halogen only, this carbon connects to the ring, so that halogens are normally considered as good leaving groups now. By leaving that carbon, right, by leaving that halogen, the carbon will connect to the ring. So what we need to add is just this alkyl halide, this section with the Br, with the halogen, Br or Cl, right? Okay, let's write this up. So this alkyl section with a chlorine to leave, when the chlorine left, right, this carbon will connect with this, right? That is normal idea, right? So that should be added with the anhydrous AlCl3 catalyst, right? So if you are supposed to come up with Br here, the catalyst should be AlBr3. If you are adding the Br here, alkyl bromide, catalyst should be AlBr3. If you are coming up with alkyl halide, alkyl chloride, Cl here, catalyst should be AlCl3, right? Okay, so let's discuss about this mechanism as well. So the mechanism, as in the earlier case, right, this mechanism involves 4 steps. Right? I'll write the 4 steps one by one. The first step is what? The first step is reaction of these two guys. The reagent and the catalyst react to form the active electrophile. Reaction of the electrophile, reaction with the reagent and the catalyst to form the active electrophile. That is the first step, right? Let's do this stuff, right? So this thing, right? This guy. So Lamai, when writing the mechanisms, it is always expected to display all the bonds with the species which are involving in bond breaking and bond forming. With the species, with the carbons involving with the bond breaking and bond forming, you need to clearly mention all the bonds there. Basically, breaking bonds and the forming bonds should be clearly mentioned, right, in a mechanism, right? Okay, that is why when we are writing the mechanisms, we are not writing the benzene like this. In the reaction, you can write the circle at the benzene, but when you are writing the mechanisms, at the mechanism, We are not supposed to write the circle here, because they are the bonds break and bonds will form. So that we have to specifically mention those bonds inside the benzene, right? So in the mechanism, don't write the benzene like this, right? Always write with the 5 bonds, the benzene, right? At the mechanism, right? This is just a reaction at the mechanism step. You are not allowed to write like this, right? All the breaking bonds and the forming bonds should be mentioned, right? At the mechanism, right? So that is why I written the carbon like this, right? So you have the catalyst here, AlCl3. What happens here? Like in the earlier case, the dative bond, right? So as this one is the dative bond acceptor, right? We can mention it as, right, a Lewis acid. So Lewis acid, right? So what will happen there? Right? So you will come up with the CH3 is there, right? So you have these hydrogens and the connected Cl and AlCl3. So as this one is a kind of a dative bond, this guy comes with a minus and this guy comes with a positive. Right? This is your active electrophile. This is your active electrophile. Your active electrophile. Right now? Okay, that is the first step. The second step is actually benzene guy attacks to that active electrophile. Benzene attacks to that active electrophile. So your benzene is there like this. That guy will attack to the so produce active electrophile. CH3 is there. C H H Cl and AlCl3 is there. This is negative and this is positive. Right? As this one is positive, this electron pair is greatly attracted towards the chlorine, so that you get some delta positive charge to this carbon. You will get some more positive charge to this carbon, some heavier positive charge to this carbon, so that towards that carbon, the positive carbon, these electrons come. These electrons come. When that occurs, this carbon will leave this bond. So chlorine leaves, right? So then what will be the product then? So this group will connect from this carbon, this CH2 carbon. This group will connect to this benzene. So I'll connect that thing from the CH2 carbon, na? From the CH2 carbon, that thing will connect CH2 carbon, and you have a CH3 carbon as well to connect to that carbon, and the other carbon gets the positive charge. When this guy, this bond comes to here, this electron comes to here, right? One carbon gets the electrophile, the other carbon gets the positive charge. That is the same thing happens with the alkene mechanisms, right? When such a this kind of a electrophilic attack coming from the double bond, right? The one carbon will get the electrophile and the other carbon will get the positive charge, right? Okay, so things will appear like this, and don't forget to mention that hydrogen here. Mention that hydrogen here, which is supposed to leave. It is supposed to leave ultimately, as this is a electrophilic substitution. When the electrophile connects, ultimately this hydrogen should leave. That is what substitution means. When the newcomer connects, ultimately the something should leave, no, which was at that place, right? Okay, so you have to write the hydrogen as well, right? No need to write these hydrogens, right? No need to write the hydrogens at the other 5 carbons, but you have to clearly mention the hydrogen appearing at the carbon which connects the electrophile, right? Because all the breaking bonds and the forming bonds should be clearly mentioned throughout the mechanism, right? So it is very important to write this hydrogen. If you are not written this hydrogen, you won't get marks for this area in mind. To get the marks for the area in mind, definitely this hydrogen should be mentioned, not the other hydrogens, but this one, which is supposed to leave, right? Okay, and what happens with this thing? So this bond electrons come to this chlorine, so the positive charge of the chlorine will disappear. So we will ultimately come up with Cl and AlCl3 with some minus here. So Cl and AlCl3, the minus on the aluminium. Or one can write this as AlCl4 minus. One form is enough, right? No need of writing both the forms. This form or this form. One form, writing one form is enough, right? Okay. The third step. Third step is stabilization of the resonance stabilization of this co-produced uranium ion. This is your uranium ion. The resonance stabilization of that uranium ion carbon ion is the third step. Let's write that thing. So let's start with that uranium ion, this one. So you have the positive charge here, the hydrogen CH2, CH3, right? They're not 11. So these electrons comes to here, right? To neutralize this positive charge. So positive charge will come to here then, like in the earlier case, right? The same process happens, right? This charge happens to come here, right? So hydrogen CH2, CH3 is there. Bond is also there. So then what will happen? Then to neutralize this positive charge, the electron pair comes to here, right? So the positive charge will come to here. Right now. So things will looks like this. Positive charge comes to here. Right now. This is the resonance stabilization of the uranium ion. That AlCl4 minus is also appearing. Right now. Third step. Let's copy the fourth step then. The fourth step is regeneration of the catalyst. Regeneration of the catalyst. This is the catalyst. No? Regeneration of the catalyst with the major product. With the major product. See how it comes. So you had the positive charge here. The hydrogen which is to leave. Right. But 11. So you have the AlCl4 minus here like this. Then with this bond, the chlorine coming to the hydrogen, and then hydrogen will leave the two electrons to form the benzene ring again, to create the benzene ring again, right? So we'll come up with the major product. Right now, with some CH2, CH3 appearing, and then the HCl and AlCl3 also will produce. AlCl3 is your what? Is your catalyst. Right now, so major product and the catalyst will be formed. Right now, so that is how you're supposed to complete the filter of alkylation. Just complete this stuff now. फिर रिवल्ट में तरफ लिया गया is secondary or tertiary alkyl halides. See, so it's like this. So same benzene appears here, right? So let's try to come up with this kind of stuff. CH3 twice CHCl with anhydrous AlCl3. This thing is this now. See, two CH3 groups with one hydrogen Cl. No, that is this. No? CHCl, CH and a Cl is there. Two CH3 groups. So this is the secondary alkyl halide, right? Secondary alkyl, right? In the tertiary as well, the same kind of mechanism appears, right? So what will be the product then? So let's come it around, right? No worries. What will be the product then? So this chlorine leaves, and this carbon converts to the benzene ring. That is the ideal. As halogens are considered as good leaving groups, that thing will leave, and with that bond, the carbon will connect to the benzene ring, right? So that carbon is appearing, that is with two CH3 groups and one hydrogen, right? Two CH3 groups and one hydrogen, right? So you can write it like this, no worries. Huh? Two CH3 groups and one hydrogen, right? Okay. So let's come up with the mechanism here. Let's try to come up with the mechanism here. Right? So first step is the reaction of these two guys, right? The reagent and the catalyst to come up with the active electrophile. So let's come up with that. So you have the CH3s. So with the carbon switch involved with the bond breaking and bond forming, you have to write all the bonds, clearly mention all the bonds, right? So that is it. The second alkyl halide, right? Reacting with AlCl3. So what will happen? Lone pair electrons will donate, like in earlier case. No difference to the earlier case still, right? So you will come up with this one. Some negative plus recharge appears here and negative charge here due to the D2 bond formation, right? So this is referred to as a Lewis acid, which accept the lone pair, right? Okay. So after producing this thing, right? At the same step, this also leaves. This also leaves by creating this kind of a active electrophile. Creating this kind of active electrophile, right? This Cl also leaves. One can write it as AlCl4 minus. So at the same state, at the first step, right? This thing also leaves. So this is the active electrophile. In this situation, this is the active electrophile. In earlier mechanisms, we took this one as the active electrophile, this stage as the active electrophile. But in this case, this is the active electrophile because this is possible with the secondary and tertiary alkyl halides. With the secondary and tertiary stuff, this is possible because they are able to form much stable carbocations than the primary. Carbocation, these secondary and tertiary guys are able to form some much stable carbocations. So that can last for a few more time, right, than the primary carbocation. So this thing will be the active electrophile with the secondary and tertiary carbocations. So with the secondary and tertiary alkyl halides, right? That is possible as secondary and tertiary carbocations are stable than the primary. So primary can't exist for a long. Right? That is why the primary carbon is not formed with the earlier mechanism, but with the secondary and tertiary are able to stand for few seconds, right? So those will be formed. So with the secondary alkyl the active electrophile is this, which is a carbocation, right? Earlier case it was not a carbocation. Earlier case it was a neutral species. With the primary halides as well as the bromination process, your active electrophile was a neutral substance. Neutral substance. As a whole, this one won't carry any charge. No? These things will cancel off. No? As a whole, this won't carry charge. No? But when with the secondary and tertiary alkyl halides, as well as with the next mechanisms we are going to study, we will come up with some charge electrophile. Some charge electrophile. So actually, these electrophiles are more stronger electrophiles than the last two situations, than the last two mechanisms. These electrophiles are much stronger electrophiles because those are carrying some positive charge, right? Okay, so this is the active electrophile. That is the only change we will see with the next mechanisms. The electrophile is completely positive charge, right? Okay, the rest is same. The rest is same, right? Okay, let's do the other stuff, right? This is the end of the first step, and the second step is what? The benzene ring attacks to the so formed active electrophile. The benzene ring attacks to so formed active electrophile. So you have this electrophile, right? So with this electrophile, you have the positive charge, and you are with some CH3 groups. So I'll write it like this. It's better to easy to follow this. So this is your electrophile, right? No worries, no same thing happen. So to that thing, so when writing the electrophile, write the other stuff as well, right? AlCl4 minus as well. So this to this, the benzene attacks. That is so produced electrophile, so that benzene attacks, right? So we will come up with the arenium ion or the arenium ion. So don't forget to put the hydrogen of the arenium ion. It is created like this. And don't forget to write the AlCl4 minus as well. This is the arenium ion, right? Then there is a stabilization of the arenium ion, right? So it's like this, no? So you have the positive charge here. Right? So this electrons will come to here. So you will come up with this positive charge, right? Right, okay. Then as these electrons come into here, the positive charge will come to here, right? So that is the resonance hybrid of the arenium ion. This is the resonance hybrid of the arenium ion, right? This is referred to as the resonance hybrid of the arenium ion, right? Okay. So representing all the resonance structures with these signs, right, is referred to as the resonance hybrid of arenium ion. If they have asked you to draw the resonance hybrid of arenium ion, just draw all this stuff, right? This thing, all the resonance structures connecting with this symbol, right, which is written to represent the resonance relationship, right? So and the AlCl3, sorry, AlCl4 minus. Finally, what? Finally, the regeneration of the catalyst with the product. Right, you have this thing. So then the AlCl4, that guy attacks. Like this to hydrogen, and hydrogen leaves this bond to form the major product, right? 2 no HCl and AlCl, right? This is your catalyst, and the majority is there, right? No? So quickly complete this stuff. Let me get this. So this is a special case, right? In this case, the first step is with 3 steps, no? Right? So this is the active electrophile you produce, right? That's very important. Number 3 is field graft acylation. Right? Let's come up with the field graft acylation, right? Okay, it's just connecting a ketone kind of a group, just connecting a ketone kind of a group to benzene ring, right? So that is the reaction. So we are supposed to discuss about the mechanism as well, right? So let's see. This is first of all, this is the reaction, right? So you have benzene, and you are supposed to connect kind of a ketone kind of a thing, right? Like this. This is acylation. That is acylation, right? To do that thing as well, first you should need to have some chlorine connected to this carbon. Some chlorine connected to this carbon, which is going to connect with the benzene ring, right? So chlorines are good leaving groups now. So if you had a chlorine first connected to this carbon, so you can leave that thing and connect that carbon to the ring, right? So then it is going to be a alkyl halide. It's going to be a not the alkyl halide. It's going to be a acid chloride. It's going to be a acid chloride, right? So having a chlorine at that carbon is like this now. It's a acid halide. So this is the carbon which is connected to the ring, right? So we are in chlorine earlier, right? So acid chloride, if an acid chloride is to react with anhydrous AlCl3, the same catalyst which has been used earlier, right? For the field graph reactions, same catalyst can be used, right? So you can copy the product, benzene ketone, right? So let's discuss about the mechanism there. Mechanism. Right? Again, this mechanism also with 4 steps, right? Like in earlier cases, right? So first step is the reaction of these two guys. Reaction of the reagent with the catalyst, right? So same kind of reaction, right? So CH3, C double bond, Cl is reacting with AlCl3. And what will happen? So like in earlier case, right? This electron pair will be donated to this catalyst. So catalyst is referred to as a Lewis acid, then accepting the electron pair Lewis acids, right? So this is a Lewis base, then this is a Lewis base donating the electron pair, right? So first you will come up with this one, AlCl3. Aluminum gets a negative charge while the chlorine gets a positive charge, the dative bond, because of dative bond, right? Then what will happen? In this case as well, right? Then this bond will leave, like in the alkylation of secondary alcohols, so secondary alkylation with the use of secondary alkyl halides. In this case also, this thing will leave and form the active electrophile with a complete positive charge. with a complete positive charge. Now onwards we are coming up with electrophiles with complete positive charges, right? ACl4 minus. So one can write the same stuff as like this as well. No worries, huh? Both acceptable, right? Okay, so this is your active electrophile bearing a positive charge on that carbon, right? Then what will happen? Next step. So attack from the benzene towards this active electrophile. Oh, active electrophile attacks the benzene. Both are same, right? Okay. So you have the benzene here. This is your electrophile. So I'll write it here like this. This positive thing, right? So with that, AlCl4 minus is also there, right? So this guy attacks, ring attacks, right? Like this. So you should have this bonds as well, no? So we'll come with this. Recharge, hydrogen here. This guy connects to here. Right now. So and the AlCl4 minus IBS, right? Okay. Both are same, right? No worries. Right, like this. So this both are okay, right? Then the third step, the resonance stabilization of uranium ion. This is the uranium ion. So produce uranium ion, which is a carbocation, right? So resonance stabilization of that thing. So when these electrons come into here, positive charge appears here. Right? When these electrons come in here, the positive charge appears here, right? This is resonance stabilization of the uranium ion, right? Positive charge appears here. This is a resonance hybrid, right? So you have the AlCl4 minus as well. Finally, the fourth step, recreation of the catalyst with the formation of the major product. Formation of the major product, right? Right, you have the Cl, AlCl3, right? So just take this one, right? Just take this one. Right? These are two guys, right? Which are to be written here, right? So just write is attacked from here, and this hydrogen will leave, making the benzene ring again, right? So major product and HCl and the AlCl3, which is the regeneration of the catalyst, right? Catalyst, right now. That's it. So that is about the telegraph phase relation, right now. Just come up with a screen capture ළමයි. ඔගේ screen capture එකක් ගන්න. දැන් ඔයාලට වැඩි තේරුණානේ මොකද්ද වෙන්නේ කියලා. ඔයාලට ඊතර දීක complete කරගන්න පුළුවන්, right? Just take a screen capture of this. මොකද අපිට තව පොඩි කැල් ටිකක් කතා කරන්න තියෙන නිසා අද බෙන්සින් ටික ඉවර කරගන්න ඕනේ, right? So just take a screen capture here. අර වගේම right ඉස්සල්ලා ගමු යන්නේ ඉස්සල්ලා වගේම වැඩි යන්නේ. So with this activated trial with this activated trial, this is a linear stuff, right? See around the carbon it is linear, right? Keep that in mind. Around the carbon it is linear, right? Okay, so you clearly see that thing here as well, right? Some sp carbon appearing, right? So mark that thing as well, that's better, no? So this carbon is sp, sp carbon linear, right? Okay, let's come up with the next one. Nitration. Benzene nitration, right? First write the reaction. First let's come up with the reaction here. Reaction is this. Nitration means connecting kind of a NO2 group to the ring. Connecting a NO2 group to the ring. That is what meant by the nitration, right? So to come up with the NO2, the reagent we use is the concentrated nitric. Concentrated nitric is the one which provides the NO2 group, the NO2 electrophile, NO2 plus electrophile, right? And as we all know, there should be a catalyst as well for all of these four reactions. Not only the reagent, the catalyst is also needed. So here, as the catalyst, concentrated H2SO4 is used. H2SO4 is used. Normally, this reaction is carried out under 50 Celsius temperature. Under 50 Celsius temperature, right? So that heat also should be supplied. If not, the reaction won't occur, right? Okay. So that is the reaction. Less concerned about the mechanism as well. Mechanism. This is also like the same, right? First thing is all about reacting these two guys, the reagent and the catalyst. Just do that thing to start up with. So you have the HNO3, here, right? This is the HNO3. This is HNO3, right? We have positive charge and the minus here, HNO3. So you have lone pair here, right? Okay. So this is the H2SO4, this is the catalyst. H2SO4. H2SO4, right? So at this first step, this lone pair will attack this side here, which is delta positive, right? So that this pair will be released to the oxygen, right? So here this can be referred to as a acid. It could be referred to as a Lewis acid as well as a Bromstein acid. Both are acceptable. Let's see why is that. So with this electronic transition, we'll come up with something like this. OH2 plus, as this guy grabs this side here, it becomes OH2. The plus appearing on the oxygen as it's a dative bond, right? And here, with that, O minus SO3H also produces, right? This oxygen will carry the minus charge with the lone pair, and SO3H, O minus SO3H. Sorry, it should be hidden here. It is H2SO4, sorry for that, right? So O minus SO3H, SO3H, O minus SO3H, right? Okay. So in this step, we can consider the H2SO4 as a Lewis acid, as it is accepted in lone pair. It could be considered as a Lewis acid as well as a Bromstein acid, because it is releasing an H plus. It is releasing an H plus, right? So both are okay, right? Lewis acid or Bromston-Lowry acid. Bromston-Lowry. Lewis or Bromston-Lowry acid, right? Okay. So here, this thing we use as a Lewis base accept in the H plus means it's a Lewis base here. This is the only occasion where nitric behaves as a base. Where nitric behaves as a base, right? It's very important. No? So then after this, what will happen? So the bearing the positive charge on oxygen is not good, and these two guys are with the same sign charges. The repulsions will occur, so that this bond will break like this. So when it happens, right? As nitrogen loses its octet, these electrons will also come to here, right? So finally, you will get what? Some oxygen like this, and positive charge is there with the nitrogen, right? As this bond leaves, these electrons are coming, so nitrogen is the positive charge, and the water is also there. Water is also leave. So no, I'll write it there. Water over here, it's better. So this is your activator file, right? This is your activator file. And here also you see some linear form with some sp nitrogen, like in earlier case. Earlier it was a sp carbon. Now here sp hybridized nitrogen, some linear species, right? No? So that is the first step, right? Okay. Then next things are same, right? Next things are same. Then benzene will attack to the so produced active electrophile, right? So you have this, right? So write the OSO3H as well. So benzene will attack to this to produce the uranium ion, right? Right now. This is your uranium ion. Right. Next is the stabilization of the uranium ion to resonance. Right. Resonance stabilization of uranium ion. When these electrons come into us here, this gets a positive charge. When these electrons are coming towards here, this gets a positive charge, right? The stabilization of the uranium ion, right? The final step is regeneration of the catalyst with the product. Right. So you have the OSO3H, O minus SO3H, that will grab your hydrogen again to create the catalyst again, right? So that hydrogen will leave this two pair, these two electrons, right? To the ring, right? That will given to the ring, so that the benzene can be created again. The ring can be created again, right? So you will create this the product and the H2SO4 again. So H2SO4 is considered as the catalyst for this reaction. It is created again, right? So it is the catalyst. Right now? So this is the mechanism. This is the nitration mechanism, right? Just quickly go through that. You can take a screen capture as well. Screen capture ගන්න ළමයි මේ පිටරටක් ගාලා ඉතුරු ටික කරගන්න පුළුවන්. So this is the only situation where nitric acid behaves as an base. Where the nitric acid behaves as a base, right? This is the only situation, right? So it's very important, right? This is very important in our syllabus. It's the only situation where nitric behaves as a base, right? Complete stuff. Right now, you check that. Hi. අපි යන් ඊළඟට වැඩි ඉවරයක් කළා දාන්න. Right? Next page, page number 33. Okay, Lamai. We have just ended the discussion about the electrophilic substitution reactions at the benzene ring, right? We just completed the electrophilic substitution reactions at the benzene ring. Now we are going to discuss about some other kind of reactions appearing with the benzene, involvement of the benzene. We are going to discuss about the other kind of reactions, right? The characteristic reaction type is the electrophilic substitutions. We had discussed about that thing. Now we will move to the other kind of reactions which are possible with the ring, right? Okay. So number two. Earlier the number one is the electrophilic substitutions, right? Number two, the second kind of reactions with the benzene ring, right? So we can think of a hydrogenation. So it is but it is done in a very extreme condition, right? So that is the second reaction. It is the right addition of hydrogen addition of hydrogen to benzene ring. Normally the addition reactions are not preferred at the ring. Normally addition of reactions are not preferred at the ring, but you can do this one. You can do this one with extreme conditions. See? So your benzene, right? Your benzene is like this, no? The CH6 benzene, right? So if you add some H2, if you add some H2 with rainy nickel, H2 with rainy nickel. Rainy nickel means activated nickel. So normally H2 nickel will be added to hydrogenate the 5 bonds in the alkenes, but here the H2 nickel won't do anything, but rainy nickel, more activated nickel. That means it is the powdered form of the nickel, highly activated nickel. Your catalyst is activated here. Some extreme conditions are used, right? And even with the use of 150 Celsius. So these conditions are very needed. With these conditions, you are able to come up with this compound, right? Which is known as the cyclohexane. Right? Cyclohexane. Right? So in the cyclohexane, right, the chemical formula of that thing is C6H12. Right? Cyclohexane. Right? You can produce that thing. So don't wonder about this thing, right? It is like this, Lama. So there is a way of drawing the organic molecules. which is known as line structures. Line structures, right? That is how they have represented this cyclohexane as well as this benzene here with the use of line structure formulas, right? So line structures means, so if you have to draw a structure like this, one line like this, right? It says at the corners the carbons are appearing. At the corners the carbons are appearing, and to have 4 number of bonds, the rest are hydrogens. The rest are hydrogens. So that this means this is equal to 2 carbons are there. At the corners the carbons are appearing, and to complete the 4 bonds, the hydrogens are also there. So this one line, this line actually represents this molecule. So think of this kind of a line structure. This means at these 3 points the carbons are appearing. These 3 points the carbons are appearing. With the first carbon you should have 3 hydrogens. You should have 3 hydrogens like this. No? Carbons are appearing. With the first carbon should have 3 hydrogens. The second carbon, to complete 4 bonds, you need another 2 hydrogens, and this carbon you need another 3 hydrogens. That is structure, right? That is referred to as line structure formulas, right? So with the use of that confirmation, they have written the cyclohexane. So this can be easily written as CH3, CH2, CH3, right? That's it. This is just CH2, but CH3, CH3. This is CH3, CH3. This is CH3, CH2, CH3. Like that. What is this? This is C is there. 2 bonds are there. That means another 2 hydrogens should be there. CH2, 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 CH2. 6 of CH2s. That means C6H2. C6H2. Even with this thing, you can clearly see. C is there. 3 bonds are appearing. So 1 hydrogen should be there for the 4 bonds. So this is CH. This is CH. CH, 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 CH. 6 carbons and 6 hydrogens. Right? If you're supposed to write like this, line structure formulas, this means here you have CH2. Right? 2 bonds are needed to complete the 4 bonds. 2 hydrogens are needed, and double bond is there. And this carbon, that is a hydrogen, 1 hydrogen, because 3 are there. The 4th bond is hydrogen, and this carbon should be with 3 hydrogens for the 4 bonds, right? Line structure formulas, right? So with the use of that, they have drawn this cyclohexane, right? Don't worry about that thing that much, right? So that can be made by adding ready nickel to H2. Some extreme conditions are needed, right? If not, you are unable to do kind of additions with the benzene ring, because benzene is not preferred to, right? Get rid of its resonance stabilization due to the conjugate double bond systems, right? So anyway, the production of cyclohexane is possible with this kind of extreme conditions, right? Okay, and it's there in the research book, right? Third kind of reaction. This is our third one, right? Possible with the benzene, right? The third kind of reaction you should know with the involvement of benzene ring, right? Third type. So the oxidation of benzene related species. Quickly, let's discuss about this. The oxidation of benzene related species. Lamai, the first thing you should know here is actually, even though the alkenes can be oxidized even with the basic KMnO4. Even with the basic KMnO4, alkenes can be oxidized, right? So you know, even with the basic KMnO4, alkenes can be oxidized. Alkenes can be oxidized even with the basic KMnO4. Forming diols, right? But benzene is not going to oxidize even with acidic KMnO4. Even with acidic KMnO4, much stronger oxidizing agent, or even with acidic dichromate, right? Even with use of these strong oxidizing agents than these, right? Still, you are unable to oxidize the benzene ring, right? No reaction will occur. As it is not with some complete 5 bonds, as it is not with some complete 5 bonds, benzene won't get oxidized. The ring won't get oxidized with the even with the strongest oxidizing agents, right? But the substituted benzenes, will get oxidized. This is discuss what this means. The substituted benzenes, like this. So if you are with a if you are with a carbon, right? If you are with a carbon, to connect to that, if you are with at least one hydrogen or a oxygen or a 5 bond connected to that carbon, right? If you are with a carbon hydrogen bond, carbon oxygen bond, or a carbon 5 bond, right? With the carbon directly connected to the ring, then if you are to add H plus KMnO4 or H plus dichromate, then what will happen? Then this carbon will get oxidized. That carbon will get oxidized and will produce the benzoic acid. Will produce the benzoic acid. Such kind of oxidation is possible with the substituted benzenes, right? This is carboxylic acid, right? So again, I'm telling you, even though the benzene ring won't get oxidized with the strongest oxidizing agents available in our syllabus, still the substituted benzene will get oxidized like this. But some requirement should be fulfilled. What is the requirement? The carbon which is directly connected to the benzene should have at least one bond with hydrogen, or at least one bond with oxygen, or at least one pi bond. Then this thing will occur, right? So if you need some examples, right? So I'll write some examples here, right? Let's write some examples at this corner. Right? Some examples regarding this one. Right? See? So you could think of alkane groups, right? You could think of this kind of stuff. See, the hydrogen, carbon hydrogen bonds are there. Or you could think of some carbon oxygen bonds. See, the alcohols, aldehydes, even the ketones. Till you are with carbon oxygen bonds and the 5 bonds. Right? even these carbon 5 bonds. All of these will form benzoic acid if you add H plus KMnO4 or H plus dichromate. Right? All of these things will form this benzoic. Right? Clear? No? That is the idea, right? So if you are with a hydrogen, carbon hydrogen bond or a carbon oxygen bond, even with benzene keto, that thing will occur, right? As you are with a carbon oxygen bond or carbon 5 bonds. Right? All of the guys will produce the benzoic acid when you are oxidize that thing with KMnO4 dichromate. Right? So according to this, the only situation with carbons which is not going to give you the benzoic acid is actually this one. When you are with a carbon which is with 3R groups, so this thing is unable to produce the benzoic acid if this thing is react with acidic KMnO4 or acidic dichromate, right? This one won't produce. No reaction. Other than this thing, right? Almost all the stuff with a carbon connected to the ring will produce the benzoic acid, right? So in this case, you clearly see the carbon hydrogen bonds are not there with this carbon oxygen bonds are not there with this carbon, as well as no carbon 5 bonds with this carbon, right? So that you won't create the benzoic acid in this case, but in these situations, you are able to come up with the benzoic acid. Even in the ketones, right? That is very important. Na? Even in the secondary alcohols, you get the carboxylicity here. Not like in aliphatic situations. In aliphatic chains, with the secondary alcohols, with the strong oxidizing agents, you get the ketones. But here, you get the carboxylicity. That is very important. Na? Right? So note that is also there in your note as the ultimate part, right? At the page number 33, right? It is said, right? What it said, just go to that. It said, right? Benzene does not get oxidized by normal oxidizing agents such as H plus KMnO4 due to its stability. So you clearly see this thing, no oxidation, right? However, the following substituted benzenes can be oxidized by KMnO4 to produce the benzoic acid. Acidic dichromate also can be used for this oxidation, right? That is what Resonce book says, right? So all of these guys are able to produce the benzoic acid, right? So ultimately it is said that mentioned in this thing, they are saying tertiary alkyl groups do not get oxidized under the conditions in which primary and secondary alkyl groups get oxidized. Right? So more vigorous conditions under which tertiary alkyl groups get oxidized also results in cleavage of benzene ring. Just correct that thing, Lamai. At the final point, it should be more vigorous conditions under which it should be tertiary. Under which tertiary alkyl groups get oxidized also results in cleavage of benzene, right? That is the ultimate idea, right now. So that's it for the benzene, right? We'll stop at this stage, right? So we'll come up with the benzene conversions next week onwards, right? Benzene synthesis process. So for today, that's it. Goodbye then. See you next week.